Inside a modern operating room, an anesthesia monitor tracks several vital signs simultaneously. While heart rate and oxygen saturation are standard, the carbon dioxide waveform provides the most direct, real-time account of a patient's internal physiological state. This is end-tidal CO2. It represents the partial pressure of carbon dioxide in the respiratory gases, measured at the absolute conclusion of a single expiration. In healthy patients, measured end-tidal CO2 reflects the alveolar PCRPO2, acting as a proxy for arterial CO2 tension. They are separated by a 4 to 6 millimeter of mercury gradient caused by physiological dead space, air entering the lungs that doesn't participate in gas exchange. Clinical practice relies on this metric to confirm airway placement, but because gas originates in the tissues and travels through the blood to the lungs, it acts as a tripartite monitor of the entire body. Understanding this tool requires looking at three core elements: the optical physics of the hardware, the chronological phases of the breath, and how emergencies distort the graph. Effectively, end-tidal CO2 is the only non-invasive metric that provides immediate evidence that cells are metabolizing, the heart is pumping, and the lungs are ventilating. To measure this gas accurately, the monitor must isolate a single invisible molecule from a complex mixture of oxygen, nitrogen, and halogenated anesthetics. The elegant solution lies in infrared spectroscopy. This technique is built on the fact that gas molecules containing two or more different atoms absorb infrared radiation at specific, predictable frequencies. Symmetrical, diatomic molecules like O2 and N2 are nonpolar. They lack the molecular structure to interact with infrared light, allowing it to pass through them without any energy loss. Carbon dioxide is asymmetric and polyatomic. This structure causes it to strongly absorb infrared radiation at a peak wavelength of 4.26 micrometers. The Beer-Lambert law quantifies this interaction, stating that the amount of light absorbed is directly proportional to the concentration of the molecules in the sample chamber. The monitor calculates the CO2 concentration by measuring the light that reaches the detector. As the CO2 concentration in the expired breath increases, the intensity of the light hitting the sensor decreases. This physics imposes a strict material requirement on the hardware. The windows of the sample chamber must be made from sapphire crystal or silver bromide. Standard glass windows would absorb the infrared energy themselves, blocking the signal and making the Beer-Lambert calculation impossible. There are two distinct methods for delivering the patient's breath to these sensors: mainstream and sidestream sampling. Mainstream analyzers place the infrared sensor directly in the patient's breathing circuit. This eliminates delay, but adds weight and dead space to the airway. Sidestream analyzers aspirate gas through a small tube at 50 to 200 milliliters per minute. This allows the hardware to be kept in the monitor itself, though it introduces a slight transit delay as the gas travels. Every CO2 reading on the screen is the result of this rapid, real-time quantification of light absorption. Beyond the hardware, we must look at the physiological origin of the gas. The resulting waveform is a chronological map of exhalation. This is the time capnogram, with time on the x-axis and the partial pressure of CO2 on the y-axis. Phase 1 represents the start of exhalation. The first gas to reach the sensor is from the anatomical dead space of the upper airways, which contains no CO2, resulting in a zero baseline. As the breath continues, Phase 2 shows a rapid S-shaped rise. This is the point where gas from the alveoli reaches the sensor and mixes with the remaining dead space air. Phase 3 is the alveolar plateau. The graph levels off as pure alveolar gas passes the sensor. This plateau has a subtle upward tilt because different regions of the lung empty at different rates due to varying airway resistance. The highest point of this plateau, reached just before the next breath begins, is the end-tidal CO2 value. Phase 4 represents inspiration. Fresh CO2-free gas rushes into the lungs, causing the reading to drop sharply back to the zero baseline. This square waveform acts as a chronological record of the respiratory tract emptying in sequence. Because this geometry is tied to exact physiological constants, any change in the shape or height of the waveform can be used to diagnose specific clinical pathologies. The repeating square wave is our reference for normal physiology. A sudden flat line indicates no CO2 reaching the sensor, signaling a disconnection. If the baseline fails to return to zero during Phase 1, the patient is rebreathing carbon dioxide. This elevated baseline usually signals equipment failure, such as an exhausted soda lime absorber that is no longer removing CO2 from the breathing circuit. While these signs involve ventilation, capnography also serves as an indirect monitor of the heart. A sudden, drastic drop in the height of the waveform or amplitude indicates a loss of pulmonary blood flow. In cases of massive pulmonary embolism or cardiac arrest, the lungs are being ventilated, but the blood is no longer transporting CO2 to the alveoli. This results in unperfused alveoli contributing CO2-free gas to the expiratory mixture, diluting the sample and causing the end tidal reading to plummet. Finally, if ventilation and heart function are both stable, a rise in the waveform height points to the patient's metabolism. A staircase rise in the alveolar plateau is an early indicator of a hypermetabolic crisis, such as malignant hyperthermia. In these states, cellular CO2 production increases so rapidly that it overwhelms the patient's current minute ventilation, causing the concentration in the lungs to skyrocket. The presence of a consistent waveform confirms the delivery of gas from the lungs to the circuit, while the amplitude tracks the right heart's output, and the baseline monitors the intensity of cellular metabolism. By utilizing the specific absorption of 4.26 micrometer infrared light, the clinician gains a non-invasive